Okay, so hey Linus, just get this is our sorry. I decided to do a video tutorial for this kind of deal because it's just easier to explain in voice than over text. So I'm just getting up the assignment so that I can kind of help. Just give me a sec. This is my first time doing something like this, so hopefully I get everything kind of synced up correctly, and yeah, hopefully this all works out well. That would be ideal. Now, the first question was to develop a function that finds the Taylor series of sine x centered at x equals pi over 2. And what you have to do first, as you can see, is you have to take your sorry, it's not zooming in for me. There we go. You have to take your Taylor series function, which is shown here, and you have to expand for sine. Now you know that sine of pi over 2 is 1, and you know the derivative, which is this fk. So you can take that and find the series all the way until it repeats itself, which is the fourth derivative. From that, you can rewrite it that that it's negative 1 to the k, because you know that this is going to be positive, but then it needs to be, there has to be a negative. So for every even, or sorry, it'll alternate. And this, of course, is just your x minus a to the k, which is right here. And this is basically these numbers. And then, of course, your k factorial has to be doubled, because when you expand it out, you're only getting the even numbers, even powers. So you need to make sure that you take that into account, and that's what this 2 is for. So as you can see, when you have k equals 0, you have negative 1 to the 0, which is 1, and this is going to equal 0. Yeah. So then you go to 1, but since we know that prime is going to be 0, we don't even have to worry about the odd powers. So we go 1, it's going to be negative 1 to the 1, x minus a. I believe this should actually be 2k. Hold on, I apologize. Yeah, it should be 2k. Yeah, so then you get the even powers as well. So hopefully that kind of makes sense. But that's where you will then be able to develop your function as it asks in the question. So here I have my function, sine Taylor pi over 2, and it takes in an array of x values, which you can just, well, I'm sure you know this, but you can initialize it from 0 in steps of, say, 0.01 to 2 pi. It'll give you that. And then you just have this stored here. This n is just how many times it's going to run through the Taylor series. So you can see here it might just do the first term, the second, or all the way to infinity terms. So to test this code, we could say sine x Taylor pi over 2 x, and then let's say we want the third. As you can see, it gives me an array. So that just proves that this is working. I would recommend you probably would just want to do that again, but with 0. It proves it works, but you're just going to the 0th term. If you did 1, you still have 629. And also this is a great way to prove that it's working, because we know that when you run through it once, it's always going to equal 1. That's it, because there's no x factor to it. So if your code gets this, then you know it's going to be working. In our function here, we have x minus a, and in the question they ask that it's centered at pi over 2, which we can assign as our a value. It's kind of like when we were doing Taylor series in Calc 123. It's actually identical to that. And this s just needs to be set to 0, which I'll explain later. So now we're going to run our series through from 0 to n minus 1. The reason you do minus 1 is because k will go to the value of n, but then it won't. Like if you just use n, it won't work very well for you. You'll get too many terms. So we want to do the summation, which is s, which we're returning as well, but s, which is 0 at the moment, times the function that we literally wrote in Word. There, you do not have to change anything for that. This period here, since x is an array, this period just means to multiply and use every term in x. So every time you have an array that you want to multiply or divide, that dot has to be before your operation. So that's the first part, making your function. It's really, really simple if you do this first, if you do this derivation first. Then it should be really straightforward. And a good way to prove that it's working is take a screenshot or something, either of all these ones. Because as long as everything stays 1, you know that it's working. So part B was use your function to make a plot of the approximations for n equals 1 to 5 over the domain 0, x, 2 pi, and include a curve of sine x for reference as well. And you know the plot function, of course, so you can literally just do x and ants. That's just what I got over there. And it should give me, it should give me a straight line, which it does. If I decided to run my function again, but with 2 terms, my answer changes, and I get a somewhat different curve. When all of these are together, you should have something that looks very similar to this. Your first line has to be a straight line, and your second order will look like it's not even a sine function at all. That's okay, totally normal. And then you can see that this red line and this 5th order, they stay together quite consistently until here. And that is what it's supposed to look like. Yeah, so this is just what the part B is asked for, really straightforward. If your function's working, it's literally just doing a bunch of plots. C, make a plot of the error in each of the approximations used in part B and find the range of angles that can be used if the error should not exceed 1%. I did a small function called hello, which takes my sum and my x values and determines the percent error. So here it's a typical percent error equation where it's actual versus, or theoretical versus what you obtain, or minus what you obtain, divided by the actual. Don't forget to use this period, as this is an array, and then you just multiply it by 100, and that will give you your error plot. So if we do that with our answer here, you can run hello. Let's just set error equals hello using x, or answer and x. So there we have error. Now if we do plot x and error, we will get a plot that looks like this. That's okay. Now we need to set our y-lim. And we use brackets, and we want it from -1 to 1. This is our 1%, so it goes -1% to 1%. And when we do that, we get something very similar to this, or you should. And this is the value of pi, and it's basically because it's so close to 0, MATLAB doesn't really know what to do, so it just draws a straight line. So you can ignore that. But what you want is this point at the top here. Here, I'll zoom this in a little bit. So you want where it intersects at 1. Okay, mess that up. But basically where it intersects on this line at 1, this is your angle here, right? X is your angle. So find these 2 points, and that's the range where you can have range of angles that can be used. So that's part 1. Pretty straightforward. The only thing that takes time is just all your graphs. You have to analyze them, label them, be sure to give them legends. Make them have a title, axis labels, and a legend. Same again for your error. Your error should look something like this. As you can see, this is your second order error. Now, this is the equation they give you to do part 2. You can expand this, and you can see that it does fit the Maclaurin series for sin x, which we are given in our notes. And that's basically what they want you to do. Just check that that is actually true. Nothing more. Now you want to develop a function. It says develop a function that uses this formulation to calculate sine of x. It should return the result and also all of the terms in the series. It should stop the summation at a value of n such that the next term in the series has an absolute value that is no more than 10 to the negative 6 times the value of the result up to that point. So I wrote that one right here. So to return multiple terms, you use this. It's also good to listen to that. So you just can use this form to return multiple results. And you're only taking in x for this one. So this is just a counter here, starting at 1 because arrays in MATLAB start at 1, not 0. This is your sum, starting at 0. And this is another counter, or sorry, this is your power starting at 1, whereas you can see in this equation, I is 1. I just switched I to k in my case. So I wrote the terms I because you don't actually have to set an array size when writing these equations. They can be varying size. MATLAB will make the array for you. So this I value is 1, and you have just your equation that they gave you. There's nothing else you have to do. Don't forget this dot. And that sets your first term in the array. Then you have to add that to your sum, of course, just because they want the result. That is part of the result. Now we have this while loop, and what it does is it takes the absolute value of this term and sees if it is greater than 10 to the negative 6 times your result, and if it is, it'll go into this loop. I had some trouble where my function was actually returning not a real number value. So this is what this if loop is for, or if statement rather. Basically says if terms II equals 0, which is the Maclaurin series, right, sign will eventually equal 0 exactly. It just breaks the function. It ends it. You might not need this. I would recommend running it without it first and then seeing if that needs to be solved. So of course next you have to up your counter because you've used 1 here, so this needs to be 2. You're filling in the next array value, and it's the same thing just down here. Then you add that to your terms and you add 1 to your II, and that's it. So then just don't forget all your ends. So to see this work, as in part C, it says use your function to calculate sine n pi for n equals 1 to 10. Make a plot showing all the terms in the series for each value of n. And another plot of the results for each value of n. So here, this is just showing that my code works. This is just the first term in the series. That is what it's supposed to look like. Made sure. Yeah. And then plot of all the terms versus n, so first through 10th terms. This is what it looked like. And then this is the summations of all the terms. I don't really know how to explain that when I'm not quite done writing it up yet. But that's what mine looked like. Yours should look probably similar. It says comment. My one comment is probably that it starts at 0 and ends at 0. These variations are just calculations around the area, because you can see they're really small, right? 10 to the, yeah, those are actually quite tiny, or large. Large? Really? I'm so sorry. They're quite large, so they're probably just calculations. You probably want to ask the TA more about that if you really want to know. And finally, we are asked the error function is a special function in probability and statistics that is related to cumulative distribution of the normal or Gaussian distribution. The error function is defined as this, just down here. It's the ERF function. It is written into MATLAB. And we just have to find the Maclaurin series for the error function. Now, it gives you a hint to start with the Maclaurin series of e to the x, which kind of helps you get this. So the Maclaurin function of e to the x just looks like this. That's in our notes that were put online by Pasha. Next, you can just expand that into its form. It's not very difficult. You just basically 1, 2, right? Pretty straightforward. Next, since up here we have e to the negative t squared, well, why not just make that e to the x and go here, right? Substitute x equals e to the negative t squared. So if we're putting negative t squared in here, we need to put it in each of these places as well. And that gives us a function that looks like this. So now we can take the integral from 0 to x of e to the negative t squared dt, and this, we just dt this, so these are just the integrals of each respective order. And then we can write its summation. Therefore, we can write the ERF function in our own terms. Don't forget this 2 pi, by the way, or 2 over square root pi. I don't know why that didn't work. There we go. Yeah, make sure not to forget that when you write out your final irf function. So we can write our irf approx, and it takes in an array of x values and how many terms you want to run it, which is part B. It says develop a MATLAB function to approximate the error function using the Maclaurin series result from part B. It's supposed to be part A. The function should take the array of x values to evaluate and the number of terms n to use in the series. Plot the result for several different values of n and compare it to the built-in irf function over -2 to 2 of x. Submit your code and testing procedure. So this is what it looks like as a function header. You just have one return value and an x array, number of series, or number of terms in the series. Then you have this r equals 0. This is just a summation start. You could also put s, whatever helps keep it in your head. Then we have this for loop running from k, or 1 to n. I know I had n minus 1 before, but this seems to work for this one, so I'm keeping it. So you have r plus, this is literally what you have in here. I did it down. I did my 2 over square root pi at the base of my code. Yeah. So then you just basically you create values of e for each one. So what you're going to want to do is, like, you're just going to return irf functions for each, and then you can plot it against the real irf function, which is the red one. And as you can see, my red, which starts over here, is very, very close to my 10th term. It'll start out as a straight line because it's just, yeah. I did 1, 4, 6, 8, and 10. And it's just because it said got the result for several different n values. There was no real requirement for anything. Then you can just comment on it, and yeah, and then you're done. So if you have any questions, let me know. I just received a phone call, so I might add a few things later. But yeah, let me know if this makes sense. I hope it does, and cheers, buddy. Have a good one.